Hi everyone, we're Team 15 and we were tasked with the project Extracorporeal Membrane Oxygenation. Now essentially what this is a medical device housed outside of the body that acts as an artificial heart and lung. And Cass will be able to tell you just a little bit more about that.
So, how does it work? ECMO is a machine that either supports lung function or heart and lung function. This can either be after a trauma or to allow a patient additional time to wait for an organ transplant. The venous arterial ECMO assists both the lung and heart function, pulling blood from a vein and returning it back to an artery. This is used more often than venous venous because it reduces additional stress placed on the heart from only supporting the lungs. Here we focus on veno-arterial since it supports heart function and the pump needs to operate at a higher pressure than it would with venous-venous. With higher pressure come increased shear stresses and increased opportunity for blood clots to form. Even though ECMO can be very helpful, there are still two major complications associated with it: clotting and the use of anticoagulants. So the ECMO device can be problematic over long periods of time. Extended duration of use promotes the blood clotting cascade. This leads to blood clots forming within the ECMO circuit and the possibility of them flowing back to the patient's body. These clots returning to the patient's body can result in embolisms or blockages that can ultimately lead to death. Another important consideration is the common use of heparin, an anticoagulant, with these devices that reduce the chance of clot forming within the device. Heparin has its own problems associated with it, such as causing unexpected and or constant bleeding, decreased blood platelets, and possible severe allergic reactions, known as anaphylaxis.
We were able to tackle these issues by changing the pump, gas exchanger, and the heat exchanger. Now, changing each individual unit operation like this allowed us to reduce the shear stress generated in the circuit, which is reported as the main cause of ECMO-induced clotting. By changing the design of the pump based on the shape of the impeller base and blades, as well as the size of the impeller, we were able to reach a solution that has minimal generation of shear stress. We compared the impeller blades using SolidWorks Flow that generated wall shear stress contour maps, shown in figure 1 to the right there. The beauty of these simulations that we ran is that we were able to keep simulation conditions constant to effectively compare how the impeller blades and the shape of the impeller base impacted the wall shear stress induced on the blood. After completing these simulations, we also decided to test how the size of the pump would affect shear stress and came to the conclusion that the pump should be enlarged compared to what it is in industry today.
In the gas exchanger, oxygen is added to the blood and carbon dioxide is removed from it. The goal here is to keep the blood above 95% of the typical oxygen saturation. By adding oxygen and removing CO2, we can prevent the patient from suffering from hypoxia and hypercapnia, which is the excess of carbon dioxide and the lack of oxygen, which can result in many respiratory problems.
A heat exchanger is needed to prevent the patient from experiencing hypothermic conditions due to the heat losses throughout the circuit. While taking the properties of blood into consideration, we find that the required amount of heat exchange is not very extensive for this process. Therefore, integrating the heat exchanger into the gas exchanger, similar to the affinity fusion designed by Medtronic, allows for a more compact device and a shorter path for the blood to travel, minimizing the possibility of clots forming. Additional modifications were made to the material and the thickness of the tubing to ensure an adequate amount of heat exchange and to minimize the accumulation of blood within the device. These changes ensure that the blood is heated to its desired temperature and that the risk of complications arising is minimized.
There is a fairly large ethical concern associated with the ECMO device. When should someone be taken off of life support? This artificial heart and lung can be a life-saving machine, but it can also be a path to nowhere. Since these machines are usually used as a last resort, there's a chance of failure and subsequently death. This raises the question, how long do we keep patients on this device without any signs of recovery? These devices are incredibly expensive to operate and keep the patient hospitalized, so physicians cannot keep someone supported forever. With price in mind, we should also discuss the approximate cost of these machines. While the machines do not have a reported cost associated with them, our approximation rates them to be around $100,000 each.
Given that ECMO machines are a very high value item, we weren't able to work directly with one, creating some of our weaknesses in the form of our quantitative analysis that we had to do on a mostly theoretical basis. We also had a limited amount of information on the current ECMO models in their size and parameters of each individual unit operation, which led to the assumptions that we had to make for the project as a whole. With more time, we would love to take this project in a direction with more in-depth modeling and hands-on testing to create a more accurate quantitative model. Along with that, we would also hope to construct a more accurate economic model to determine how our design fits into the current market.